everyone. I'm going to be going over some problems that people have emailed me. I've got 3 of them here in case you want to skip ahead to different problems. One of them is finding the volume of a solid bounded by 2 surfaces. And the next one is somebody just asked a general question about visualizing things in rectangular coordinates. So I'll talk about that next. And then the last one is finding the mass of a solid. So that's from section 15.4, I believe. But starting with this first one, it says define the volume of the solid inside the sphere like this, outside the sphere like this. I'm going to draw a quick sketch of this. It's always a good idea. Again, I haven't prepared these other than writing them down, so you're getting sort of the genuine office hours experience. And I'll try to explain everything that I'm thinking while I do this problem. So let's see, this sphere has a rho value. So x squared plus y squared plus z squared is equal to the radius in rho squared. So we have a sphere radius 6. So put a little 6 there. And it's going to be inside that sphere, and it'll be outside the cylinder. X squared plus y squared equals 4. And if I look at this from the top-down view, then x squared plus y squared equals 4 is this circle, radius 2. So that means that I'm looking at everything outside this cylinder. So the solid that I'm looking at is going to be sort of this sphere of radius 6 with a diameter 4 hole drilled through it, like that. Okay, so we want to find the volume of this surface, the volume of the solid, and it's telling us, let me just look this up again, because it depends on what section we're working in. Be right back. Okay, so this is from written assignment 6, so I think this is before we start doing anything with rectangular or cylindrical coordinates. So I guess I'll do this both ways so you can see kind of different perspectives on this problem. We're just trying to find the volume. So the volume of this thing, one way to think about it is if I split this in half, then the volume of my solid is just going to be double this top part here. So if I think about the top part here, this is going to be 2 times, and then the volume of this solid, you can say this is the region over which we're integrating of this is the volume under the surface. So the surface that we are finding the volume under is the sphere. So we get that z is equal to, let's see, 36 minus x squared plus y squared square rooted. And that'll be dA there. Okay. So my region, I think I'm going to use polar coordinates, and I can think about, what this shadow is going to look like. That is what gets cast on the xy plane. And in polar coordinates, if I change this to r dr d theta, then my r is going to be in between, so it starts at 2 and ends at 6. And my theta is going to be from 0 to 2 pi. This piece here, I want it in terms of r and theta. So I'm going to say that this thing is square root of 36 minus r squared. It is looking like, yeah, it's looking like cylindrical coordinates is what we're going to have to do for this one. I don't think this is going to be particularly fun to integrate. Let's see, times r. Oh, I suppose you could do it. This is a u substitution. So this would be 2, 0 to 2 pi. And then I'm going to let u be equal to 36 minus r squared. So that means that du is going to be equal to negative 2r dr. So r dr is going to be equal to negative 1/2 du, so that's the substitution I'll make. Let's see, so negative 1/2 du, I'll put that out in front here. Well, let's not do too many steps without writing this out. So this is square root of u. This is negative 1/2 du, replaces this piece here. Then we have d theta. My new bounds are going to be, for the bottom here, 36 minus 4. So that's going to be 28. Wait, 36 minus 4, 32. And this top piece here is going to be 36 minus r squared, so looks like 0. Okay. So that 2 there is going to cancel out with this negative 1/2 to become negative 1. So this is going to be the negative integral from 0 to 2 pi. (32 to 0 of u to the 1/2 du d theta. Okay, this one's looking a lot more manageable. Okay, so v 0 to 2 pi. This is going to be, let's see, u to the 3/2 times 2/3. So I'll put that 2/3 out in front here. Evaluated from 32 to 0. So that'll cancel out that negative sign, I'm sure. D theta. So this would be negative 32 to the 3/2. This was a WebAssign problem, so as long as you're not using algebra and stuff like that, I think they probably want you to keep it in this form, or maybe this will come out to be something nice. But I'll use a calculator for that in a second. The only thing I need to do, so I don't have any theta terms in here. when I integrate this, it's going to end up becoming theta. And I'll evaluate that from 2 pi to 0. So a quick way to do this is just I'm going to multiply everything by 2 pi. So it looks like my final evaluation is going to be positive 2 pi times 2 times 32 to 3/2 divided by 3. So a nicer form might be 4 pi over 3 times 32 to 3/2. Okay, so that's that one. I'll show the setup for cylindrical coordinates on this one, but my guess is that it'll play out exactly like it did here. So for cylindrical coordinates, we've got let's see, a triple integral here. 1, all right, for triple integrals. Then we have dv, and this is over my solid. So my solid if I break this up into the components for cylindrical coordinates, looks like this. Okay, so z, if you want to picture this, and I'll talk about this in the next example as well, but for cylindrical coordinates, the first thing you're going to do is think about what your z surfaces are on the top and bottom of this solid. So I like to start at sort of the positive infinity z, so like way up here in space, and then I'm going to drop a line through this. The first surface that I'm going to intersect is the top half of this sphere, and then the bottom is going to be the bottom half of the sphere. So it never touches any other surfaces as we pass through that solid. And in this one, you may have noticed that what I really should have done is say plus or minus this when I said z is equal to plus or minus 36 minus x squared minus y squared. And I'm seeing now that I should have parentheses here. But the plus refers to the top half of the sphere, the minus refers to the bottom half of the sphere. So anyway, those are my two surfaces that I'm hitting. So the